Okay, folks, so let's get started. All right. So let's get started. So this is lecture 10 of ECE 3311, Principles of Communication Systems. All right. Actually, let me minimize that. And let me close that. All right. So, okay, now we're cooking. So this is going to be an exciting lecture because we're making the transition from baseband communications to passband communications. And this is actually a very, very significant leap because we're effectively going from one type of communications that we see in things like automotive car harnesses and let's say Ethernet and other forms of guided or wired communications, and communications that is performed in an unguided manner, like in the wireless domain. Like so very excitingly, things like 5G or Wi-Fi. That operates using a passband waveform methodology, right? So before we continue, I do want to recap what we covered in lecture 9, all right? So all important recap. Okay, so lecture 9, and there's a reason why I'm emphasizing lecture 9, because lecture 9 has some really critical elements associated with it that we see consistently through all forms of communications, as well as in general, any form of signal processing, right? So let's lecture 9 recap. Okay, so we saw in lecture 9 the requirements, the Nyquist criterion for 0 ISI. So this came about right because of this. We have our pulse shape, h of t. So if it's polar or unipolar or Manchester, we had these waveform shapes, goes into a transmit filter, ht of t. So h of t, ht of t, channel filter, hc of t, and then receive filter, hr of t. And then we have the output. And what we're trying to achieve here is this idea that we want end-to-end an equivalent pulse shape, he of t, that allows us to eliminate ISI and sort of minimize distortion. All right. So with that in mind, right, this is where the Nyquist criterion for 0 ISI kicks in. So what this is trying to do is it's trying to specify what your HE of t needs to look like in order to not have ISI end to end, from the transmitter to the receiver. Okay, and this is what the criterion says. Just to recap, HE, okay, K is an integer, TS is your sampling period, plus tau, that's sort of the timing difference between the transmitter and receiver, like if the clocks are off. And this is equal to 1 at k equals 0. We're assuming at k equals 0, that would mean he tau, right? At that instant of the end-to-end equivalent impulse response, right, between transmitter and receiver, less the time difference, we should, like, that should be our target timing instant. We want to collect what is the value of the amplitude at that exact instant. And every other sampling instant, okay, should be equal to 0, right? So this is quite desirable. So there's one point, okay, that, like, so first of all, we're sampling the incoming analog continuous wave at the receiver, right? And the resulting impulse response, at the end of the day, if we sample at the right point, because we adjust the difference between the clocks at the transmitter and the receiver, right? The desired point, we should have the value we're seeking. And because we're sampling, every other sampling instant should be equal to 0 for that desired value. Of course, don't forget, we're sending a continuum of data. So if now we shift by TS to the next symbol, we should get its desired value and everything should be sampled to 0. So what this does is eliminates any sort of interference contributions, right? Like unwanted contributions that spill over from other symbols, hence the intersymbol interference, right? This is the time representation, time domain representation. Of this Nyquist criterion for 0 ISI. For the frequency, okay, if you take the frequency response of this, it will look like this. So if you take that HE, okay, of t, you take its Fourier transform, and you do the following. You take that frequency response, HE of f, okay, and you take integer multiples, frequency shifted versions of it, right? Like what I discussed yesterday. This should equal 1. I didn't have the 1 over TS, otherwise it would have been equal to a constant, right? But it should be equal to 1 for all frequency values, right? So in the time domain, your waveform, once sampled by TS, should look like this. Okay, and in the frequency domain, so that's T, right? And in the frequency domain, it should be like that, right? For all frequency. Very, very important. So this is now how we design our pulse shapes, okay? So, sorry, the end-to-end equivalent from transmitter to receiver, right? So this would give us 0 ISI. Awesome. Now, we also looked at sync pulses, and we're familiar with those, and we described why they're impractical. But then we looked at raised cosine pulse shapes, right? Pulse shapes. Very important. I'm going to put the frequency representation here. There's also a time domain too, all right? So what we get is something that looks like this. All right. And eligibility. Yep. B and greater than B. All right. And graphically, I drew one roll-off factor, but that's kind of important. This R, okay, there's an R that I defined, and that's called the roll-off factor. Okay, because what happens is, as a design tool, we have access to that. We can shape our cosine pulse shape, right? So we have 0. Very importantly, I'm going to highlight out F naught here. Okay, and that's our 6 dB bandwidth. And then we can vary the amount of absolute bandwidth B by the roll-off factor, right? So we could have something like this, So I'm going to choose, let's say that's the 6 dB point. That's our transition band. And that's each thing here, this segment here. So that's our transition band, right? That's, sorry, minus F1. That's F1, F0. And then what we've got, here's our absolute bandwidth, right? But let's say that's for a roll-off factor of 0.25. I could mess around with that. I could make something, I could increase the absolute bandwidth and get something that looks like this. Right? So now that's my new absolute bandwidth. F0 stays the same, and F1 changes too. Okay, awesome. And let's say that's R equals 0.75. So I can mess around with these things, right? But ultimately, this raised cosine pulse is also Nyquist and is practical because it can be defined in a finite manner. And we actually see this used in a lot of communication systems. You are going to most definitely see this in communication systems and if you continue and grow and evolve into a communications engineer. All right. So with this, all right, you might ask, okay, how can we make a question out of this? And that's a very good question. Here's the answer. So let's dig into a couple of questions, because this is more than a recap. This is like I really want to kind of finish off the this shucks. What I want to do is I want to go to, first of all, a question from the, wait, behave. Boop, 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 boop. Of course. So what I want to do is I want to go, just before we go into lecture 10 and passband waveforms, I want to do from the textbook, question or problem 3.46. Okay, and the question asks, so find the PSD, right? Find the PSD of a waveform. Okay, waveform output of a waveform output. Yeah, see, English is not good. So of the resulting from an Arcos. Remember, Arcos is just shorthand for raised cosine. With, again, that means with. If I put W/O, it means without, with a roll-off factor of 0.5, correct? Yep. When the input is what? Polar non-return to zero waveform or signal. Okay, so this is actually cool. This is actually super duper cool. We're making some assumptions here. Equally likely ones and zeros. Okay, very, very super important. And the other thing we're making an assumption here in general is that the channel bandwidth, okay, BW means bandwidth, channel bandwidth is just large enough to avoid ISI. Okay, cool beans. So this is really important. So what this means is, so let's decode this. PSD, all right? So power spectral density of the output. So let's look at this. I have a system. Here's our cos. The roll-off factor is 0.5. I have an input, okay, PSD, okay, that's polar NRZ, and it's 50-50 ones and zeros. Okay, cool, great. And the question is, what's the output PSD? You know what this sounds like? This sounds totally like we have like an LTI system, and we have these PSDs. We looked at this exactly like this before, but we don't have to worry about autocorrelation. Why? Because, so first of all, what we need, here we have the RCOS. We're going to need its transfer function. That's well defined, right? We're going to need the PSD of the input. That's well defined. And we know that the relationship between the two, okay, what is it? It's going to be, let's say, the PSD of the output is going to be equal to the magnitude squared. So I'm gonna do a little bit better nomenclature. I'm going to call it RCOS, right? It's going to be that RCOS magnitude squared P polar NRZ F. Okay, great. So there are a number of things we have to pay attention here to. So first of all, this, if you look in your course textbook, where is it? And equally likely, correct? Yes. So what we got here is we have the following. This is going to be equal to, this is from equation 3-41 in your textbook. This is going to be equal to whatever the amplitude squared. TB, remember, this is a binary, right? So TB, TS, mu. So I'm going to say TS, okay? Interchange the two. And it's going to be sine this guy. TS. Okay. And that's going to be TS. Correct. So that's that guy. This guy, just inside the brackets, what is that going to be equal to? Let me bring it back. This is going to be equal to H of F and that's going to be 1 plus cos pi, and then magnitude of F minus F1 over 2 F naught. Oh, no. No. My bad. It's F delta or delta F. My apologies. See, this is what happens when I base things off of my really awful handwriting. Delta F. It's the transition area. Shucks. Sorry, folks. So then close brackets, 0. Very important. Very, very, very important. And that's magnitude of F less than F1. This here is from F1 to the absolute bandwidth. Okay, and that's greater than the absolute bandwidth. Okay, cool beans. Now, okay, this is cool. This is totally cool. Now we need to figure out, okay, two things. So what is the magnitude squared of this? Okay, no problem. Like we take this thing, okay, and just take the magnitude squared. Remember, the magnitude here is 1, but all these values starting from minus b to b and everything gets squared. That's not what I'm worried about. What I'm worried about, okay, is this thing of this question never asked what's, or told us, at least not directly, what is the value of B, right? All the question asked us, okay, and you're probably going to get the exact same questions, right, is the channel bandwidth, okay? So channel bandwidth is just large enough to avoid ISI. Okay, so that's going to be really important. So what ends up happening is you're going to have this expression, right? And so what's going to happen is, okay, right, what do I do? So what we have is this expression. So for maximum bit rate without, right? That's my without, okay? ISI, right? What we need is this expression. So in the book, this is equation 3-74. And there we define this, like it's D. D is the symbol rate. But very important, very, very, very important. Remember here, one symbol is equal to 1 bit, right? One symbol duration is equal to 1 bit duration, right? 1 bit's contained in that. So D and R is interchangeable, is equal to 2B, right? 1 plus R. That's the roll-off factor again. Okay, this is very important. So what this tells me, okay, this is a very, very, very important expression. I'm gonna. So what ends up happening is, so you have that absolute bandwidth, but hold the phone, that's not going to be the bandwidth of your symbol rate, right? So when you use a raised cosine pulse, sure, your raised cosine pulse or your raised cosine bandwidth is going to go from minus B to B. But in terms of what is supported in terms of the data rate without any ISI, it's this expression. So what you're doing is you're actually normalizing against sort of the tail ends that are actually going beyond minus F naught to F naught, right? The 6 dB bandwidth. So what ends up happening, this fella here, okay, and suppose here we define that. We know that R is equal to 0.5. This means we get 2B over 3 over 2, which is 4 over 3B, which means that B is equal to 3 over 4R. So that's the bandwidth that we have here, given the bit rate, right, which is equal to the symbol rate of the polar non-return to zero transmission. All right. So now, oh boy, I'm just not done with this yet, and I'm not. So what we're trying to do is sort of build out what are the specific parameters we need in order to design the raised cosine pulse shape, okay, in order to have the zero ISI condition. So now, okay, so we got this. Yay. In terms of whatever polar non-return to zero bit or symbol rate is being deployed, okay? So this is going to define what the raised cosine pulse shape is going to look like. So what else are we missing? Well, so first of all, what I would like to know is what is that F delta, okay? So that's also, let's take another slide for that. So F delta, okay, is going to equal B, the absolute bandwidth, minus F naught. So that's the amount of bandwidth from the 6 dB bandwidth out to the absolute bandwidth edge, okay? So that's going to be equal to what? That's going to be equal to the following. That's going to be, oh, so don't forget, here in this transition, we're going to pull a little trick. Roll-off factor. Remember, roll-off factor is the transition bandwidth over the 6 dB bandwidth. Okay, so that's going to be equal to B minus delta F. Oh, look at this. Awesome. And then that in turn, folks, okay, if we do a little bit of manipulation, is R F delta is equal to RB minus F delta. Therefore, F delta, so we're playing around here. Okay, this is cool. Oh boy. So now we have this. So if we isolate for B here, we get that. Great. That's awesome. And now, what do we get if we now put this in terms of the bit rate? It's going to be equal to, so we plug in what B is, and we get 1/4 the bit rate. Also cool. Great. So now, next step. What is F1? So everyone should be seeing that I'm scaling this, I'm scaling this, I'm scaling this. So F1 is going to be B minus 2 delta F. So just as an aside, let's look at this. Right, what am I doing? Right, so that's F naught. That is F1. That is B. This here, the distance between that and that is F delta, right? And 2 F deltas, because remember, this also is equally spaced as like from F naught to B, from F naught to F1 is also F delta. So from B to F1, it's 2 F delta, hence this expression. So if we work this out, it's also 1/4 R. So cool, so cool, so cool. So at the end of the day, what we can do, and I'm not going to work this out, you plug in the expressions for F1, F naught, B, okay, and F delta into H R cos of F, okay, to have something, to have expression in terms of R. All right. So this is actually really powerful stuff. Why are we doing this? Why are we doing this? Why do we need this in R? Why do we critically need this in R? Because, you know, the end result, I'm just going to put the end result, but I'm leaving it to all of you to work this out and ask me during my office hours, you know, like, how the heck did you get that, Prof? And okay, and I'll explain. So you get this, F over R, okay, awesome. And you get this, right, and boop, boop, boop. Why do we care about expressing it in terms of R? Sorry, that's a 4. And here's the reason why. Because of this. I should have used a different color. Because of this guy. Right? Because the thing is, the PSD of the polar non-return to zero pulse shape is defined in terms of the period, or what's this, right? So symbol rate or bit rate or whatever. So what is that equal to in terms of the power? What in terms of the period, symbol period or bit period? You get it, right? So what we want to do is we want an apples and apples multiplication, because once we know how this looks like in terms of R, and we know already how this looks like in terms of R, we can then do the multiplication to see what the resulting PSD is going to look like. That's why. That is why we're putting everything in terms of R. Okay? All right. So that is question, again, 3.46. So try out the rest of this problem. But this is why we spent so much time at the beginning of this course, especially in lecture 3, when we talked about PSDs and LTI systems, because the way we represented communication systems in terms of H of Fs and H of Ts and input PSDs and output PSDs, this is where it's paying dividends. All right. So, but I think if there was a walk-away equation from all of this, if there was something also from lecture 9 you need to pay attention to, it's going to be this expression here, because of the absolute bandwidth of the raised cosine pulse versus the achievable data rate with 0 ISI that you can use given the raised cosine pulse, because of those the sort of ends of the raised cosine pulse that that you might say, oh, well, that's my entire bandwidth. No, you can't. No, you can't, right? So this, no, you can't. Conceivably, your equivalent pulse shape, if you didn't have a raised cosine pulse, would be contained within like minus F naught to F naught. Okay. So I'm going to switch gears. Okay. Whew. I know, that's a lot on lecture 9. Lecture 10, this is going to be a little bit shorter, I promise you all. All right. So lecture 10, passband waveforms or bandpass waveforms. Okay. So no, seriously, let's actually go back to here. So this is bandpass waveforms. So what's important about this? Well, we just saw it in lecture 9, right? For instance, like, what have we seen so far in this course? Well, just like what we saw 30 seconds ago, we've seen PSDs and filters and everything that are centered around 0, right? We've seen things like this. We've seen R cosine shapes in the frequency domain centered at 0 hertz, right? 0 hertz, which we call DC, right? And so there's so another way of saying it is these signals, these waveforms, everything, okay, if there was a carrier, would all be located at 0 hertz, right? So we have that spectrum. We also have seen things like this. Right? And where are they centered at? 0, right? That's F. So again, 0, centered at 0 hertz, DC. So these things we've seen so far, and everything else, the line codes, PAM, PCM, all that jazz, all at 0 hertz. Everything is centered at 0 hertz. Maybe we did move things to some minus FC and FC, but it's relatively, let's say, a small modulation to those frequencies. Like, what we're going to do now is we're going to look at taking that information and moving it to frequencies really far away from 0 hertz, okay? And we call those bandpass waveforms. So up until now, things like line codes, okay, PCM, PAM, all those things, baseband. So if anybody ever tells you now baseband, these are signals that are, if you look at the frequency domain, are centered at 0 hertz. Now what we're going to look at is bandpass, or AKA passband communications. Okay. And there is a very there's a very important mathematical relationship that I want everybody to pay attention to with this. And it's this one, equation 1. Like there's some other forms of representation here, but equation 1 is huge. Okay. And I think you're pretty much going to see this off and on throughout the rest of the course. So just a heads up, right? So let's see, VG, yeah, okay, fine. Nope, let's go here. So I'm going to put on one slide because it's that important. So definition. So this is going to slightly deviate from what you see in the slide. So VT, this is your passband signal. Passband, or if you want to call it bandpass signal or waveform. This fella here, this is what makes a lot of people nervous. So this is the real operator. I'm going to get to it in a second. Okay, squiggly brackets. So this is where I'm going to deviate a little bit. So you see it in the slide as G of T, right? I'm going to put a little space here. And then you see this, e to the j. Instead of omega c, I'm going to put 2 pi fc of t, right? This here is what we're going to call our carrier frequency, right? So bandpass or passband communications implies that the ultimate signal has been modulated up to and is centered at minus fc and plus fc, right? So here, this fella here, the way I expressed it in the slides is G of T. I want this to be a little bit more insightful of what exactly it's doing. So I'm going to I'm going to modify the representation just a tiny bit. I'm going to call it G of M of T. You might say, what the heck is that, Professor? This is what the heck it is. So M is your message signal. Okay. And then G, okay, of whatever that thing is, let's do G of M of T. Like, I don't want to confuse. G of M of T. So mapping of message signal, M of T, to baseband. So this is before we modulate it up to passband. Representation. So this is very important. So the notation here, what it means is that M of T is some form of information. In this course, we're going to have a ton, well, not a ton, but we're going to have a lot. We're going to look at, first of all, analog messages, amplitude modulation, AM, like AM radio, FM. FM radio is a good example. There's also something called phase modulation and vestigial sideband. There's all these types of techniques that take analog information, not digital, analog, but it's located at baseband, maps it by a certain representation, and then moves that information up to passband, right? Exactly like AM radio. And then there's also going to be the digital form, right? Like what we use in cellular telephony or Wi-Fi. Like, for instance, phase shift keying, PSK, amplitude shift keying, ASK, and all that. Okay, so just be very mindful of this, this is going to be an important relationship. Now, what I want to do, and let me first see. Perfect. And what I want to do now is, so this here is super important. So this, I'm going to call it a mapping function. And we're going to see a lot of mapping, okay? This modulates. And this real operator is kind of important. So this is how a real operator works. So suppose you have x and y. These two are both real. But then I have z, and z is complex. Okay? And what j here is, j is equal to the square root of -1, okay? So the way real works, there's also something called imaginary, right? So real of z will give you the real component of z, the real value of z. Now, pay attention to this one. There's also the imaginary operator. And it will produce the imaginary component of z. But this is where you need to pay attention. The imaginary operator produces an output that's actually real. It's only y. It's not jy, it's y, okay? A lot of people make that mistake. So imaginary operator spits out only the y, not jy. Okay. So you might say, so what? Well, here's the so what. Because let's say we go to this fella here. So let's go back to, okay? And then we have, I'm going to go back to simple notation, all right? And then e to the j 2 pi fc of t. Okay, holy smokes, what do we do now? So remember, like, beginning of this course, I was always saying Euler's relation, Euler's relation, Euler's relation. This is exactly where you bring in Euler's relation. So what you do is you do cosine 2 pi fc of t plus j sine 2 pi fc of t. Now, we don't know what this mapping function is. Is it real? Sorry for the typo. Or is it complex? If it's real, oh, then it's super easy, right? Because what's real times a real? It's a real value. Real times imaginary? It's imaginary. The real operator will then take of that product only the real component. So we discard basically anything that's multiplied by j sine blah, blah, blah. On the other hand, if g of t is complex, it's going to have a real component, an imaginary component, and now you've got to do you're going to have to do the product of both real and imaginary, and it gets kind of messy. So you're going to have real times real, it's going to be real, real times imaginary, it's going to be imaginary, and then imaginary times imaginary, it's going to be real, right? And then you only take the real components out. So that's what makes all of this manipulation very complex. Now, what we're going to be looking at, so look, like, you know, so just as a heads up, so look at, very importantly, in your textbook, table 4-1. So that is beautifully laid out, okay? So table 4-1, it's going to give the name of the modulation type, the pass band. So I'm going to call it PB, not peanut butter, pass band. Okay, PB name. Then it's going to say, this is how you map message. Okay, so it will provide you with the mapping function of m of t to the baseband representation. And then what it's going to do is it's also going to provide this other thing. And you might say, what's this other thing? This other thing is the quadrature modulation. And you might say, what the heck is a quadrature modulation? And now I'm going to go into that right now. But what's going to do is you can either represent the mapping function this way, or what happens is you can also break this down. Actually, and don't forget, table 4.1 spans 2 pages, right? It spans pages 242 to 243. So pages 242 to 243, okay? And what it also provides is x of t and y of t. So just a heads up. So what are these quadrature components? So let's switch gears back to my slides. Okay, so this is what I mean. So what happens is I could there are 2 ways I can do this thing. So what I can do is like, given I have a real operator applied to this complex number, what I could rewrite this in terms of a magnitude phase representation, right? So how do I do that? Well, just like we do the difference between like Cartesian coordinates to magnitude phase, magnitude is going to be the square of the real plus the square of the imaginary, and sum them up and then take their square root. And the phase, well, that's going to be equal to the imaginary component divided by the real component, and then we take the arctan of that. Okay, and then the IQ. Okay, so that's the thing. That's magnitude phase, and then you're going to hear this a lot. It's going to be called IQ. Okay, and the IQ representation in phase and quadrature is that Cartesian representation I was telling you about, and that's what table 4.1 also provides. Okay, so what happens is if g of t is equal to, the mapping is equal to a real and imaginary component, the real part is the in phase, the imaginary is the quadrature, and we can manipulate them these ways. Okay. Okay, and this is another way, like equations 4 through 7 explicitly go through that mapping I just mentioned. Okay, so I kind of took the cat out of the bag just before. So these are some of those mapping functions. Like that's what, like in fact, tomorrow's lecture, we start with amplitude modulation. So the entire lecture is going to be dedicated on how to do amplitude modulation, okay? And G of t, how do we play with it? How do we get the waveform? What are some of the particularities of amplitude modulation in this format? But there's also going to be phase and frequency modulation. And then we'll go into some weird, I don't want to say weird because that's not nice, but things like double sideband and single sideband. There's even something called VSB, or vestigial sideband. So these are some really cool waveforms. We'll also get exposed to something called the Hilbert transform, which is used in those types of situations. Okay. And then in terms of spectra, so very importantly, what we're going to have in terms of spectra is, because it's passband communications, let's look in particular at the PSD. When we look at the PSDs, so remember that's 0 hertz. We're going to have waveforms located here and here. Okay? And that's the PSD. But this is the interesting thing that we'll be exposed to. So what happens is, so let's say that mapping function, we have that baseband representation here. And let's say it looks like this. Let's say it looks like these 2 triangular thingies, right? At 0. And that's like G of F. Just like what I showed you here. Whoop. Yep. Here, G of F, G of F. So that's the frequency response of the mapping function, right? And so we also have a power spectral density associated with it. So let's bypass. So this here This here is P, G of F. But what happens is, through the process of the going from baseband and that modulation business I was telling you about, to get the passband signal, so P, V of F, we end up getting, that's F, not T, we end up getting something that looks like this. Ah, not zero, silly me. So plus FC and minus FC. So what effectively happens, that process of multiplying against a complex exponential modulates over to the carrier frequencies. Modulates to plus minus FC. Okay. So let's switch back to this. So that is lecture 10. So what we've experienced is, this is really, this lecture really provides a mathematical framework that we're going to be applying to all the analog, and later on in this course, all the digital waveforms that we'll be studying throughout ECE3311. So the sort of course of action that we're going to be taking for the next three weeks is going to be the following. We're going to be looking at how does AM work, FM, PM, VSB, DSB, SSB. Okay, so that's already 6. Then we're going to, in the middle of all of that, because there's going to be, what we're going to look at is phase lock loops. So we're going to have all this modulated carrier stuff, but what's going to be critically important is how does the receiver, first of all, track or lock onto those carrier frequencies, right? And is able to, oh, okay, you're at that frequency, I need to demodulate you back down to baseband. So that's really critical. The receiver can't operate at passband. It cannot just say, oh, extract information at FC and minus FC. It can't do that. That's going to be very expensive for a number of reasons, which I'll talk about later on. What happens is you have to demodulate back down to DC and then take the baseband signal and remap it to the message signal, okay? And in order to do that, you're going to need to lock on, and that's where the phase lock loop kicks in. Okay, so there's going to be several lectures on phase lock loops, squaring loops, Costas loops. And then we'll go into the digital version of all these mappings, like PSK, ASK, FSK, and the like. Okay, so that, folks, concludes lecture 10 of ECE 3311.